I welcome all of you to this video lecture series on fluid mechanics. This lecture corresponds to the topic 2 on fluid statics. The title of this lecture 8 is Governing Equations and its Solutions, which corresponds to the second subsection of the topic on fluid statics. The governing equation in fluid mechanics is a differential equations. We are starting here with fluid statics and later on we'll derive governing equations for fluid dynamics. So here the governing equation is presented for stationary fluid and later on we'll extend it to fluid in motion. However, for both the types of governing equation, the starting procedure is very similar, where we take an elemental control volume. Like if we are deriving in Cartesian coordinate system, let us suppose a 2D Cartesian coordinate system, then we take a rectangular control volume, a rectangular fluid element with delta x in the x direction and delta y in the y direction, and we basically apply certain conservation laws. In fluid dynamics, we'll apply both mass and momentum conservation, but here in fluid statics, we'll apply only the momentum conservation. And using the law, finally, we apply limit delta x delta y tending to 0 and obtain a differential equation whose solution is a functional relationship. So here in this case, for fluid statics, we will derive a first order ordinary differential equation, and the solution will correspond to pressure as a function of y, which corresponds to the height of the fluid. Let us start this lecture with the conservation law. Although there are two conservation laws for fluid mechanics, mass and momentum conservation law. Momentum conservation law is used in fluid statics to determine the pressure distribution in a stationary fluid. This is the conservation law which is used for fluid statics. Now, to derive the governing equations for fluid statics, which will lead us to the analytical solution for pressure distribution. In a fluid mechanics, we consider a small fluid element, and finally our governing equation is a partial differential equation or an ordinary differential equation in fluid static case. And to derive that, we take a fluid element, and finally we apply a limit delta x delta y tending to 0 to get a derivative term. So this shows the elemental control volume with delta x and delta y. Note that in a Cartesian coordinate system considered here, x is the horizontal direction, y is the vertical direction. So we consider the various surfaces which are shown here. It's a Cartesian control volume consisting of two vertical surfaces and two horizontal surfaces. This surface is called as x, and this surface is called as x plus delta x. The bottom surface is called as y, and this top surface is considered as y plus delta y. So if we represent pressure here, we represent pressure with a subscript corresponding to the surface, which is x. And here we express it as a P at x plus delta x, here P at y, and this pressure here is P plus delta y, pressure at y plus delta y. Now, in the previous lecture, I had mentioned that the pressure is at normal and compressive. So accordingly, the pressure force is shown here. These are the pressure forces which is acting normal and compressive for the various surfaces x plus delta x, which corresponds to the vertical surface, y plus delta y, which corresponds to the horizontal surface. Along with this pressure, there is a gravitational force which also acts, which is expressed here as the product of the mass and the acceleration due to gravity. In this problem, since the fluid is stationary, the viscous force and the inertia force is equals to 0, as shown here. This is the inertia force, and this is the viscous force, which are 0. So when we apply the momentum conservation law, basically we have to do a force balance. And in a momentum conservation law, we always do component by component conservation. So if you do conservation of forces if you consider the force balance in the x direction, here we apply sigma fx equals to 0. And in the x direction, the gravitational force acts in the vertical direction. So we basically get the balance of this pressure force and this pressure force. Note that all this pressure in the various surfaces is multiplied by the surface area, which is delta y for this vertical surfaces. So you have a delta y here and here. And the horizontal surface, the surface area is delta x. the size of this control volume perpendicular to this plane is taken as unity. So that's why the area is delta y into 1, and here it's delta x into 1. So if you do the force balance in the x direction, you end up with P at x equals to P at x plus delta x. So this indicates that the pressure on a horizontal layer, pressure is not varying along the x direction. So on a horizontal layer, pressure remains constant. Now, if you apply the force balance for the second direction, that is y sigma Fy is equals to 0. Now, in this case, the gravitational force will appear and you will get this expression. This is the pressure force acting in the upward direction. This is in the downward direction. So that's why there is a negative sign. The gravitational force also acts downward, so it is a negative sign. Now, if you divide this whole term by the volume of the control volume, which is delta x delta y, you end up with, and if you take this term from the left hand side to the right hand side, then you get, and if you divide by volume, the delta x is the surface area. Surface area divided by volume gives you a length scale in the denominator. So if you multiply this by delta x delta y, delta x cancels down from the numerator, and you get, if you take it to the other side, right hand side, you get P at y plus delta y minus P at y divided by delta y. And if you apply limit delta y tending to 0, which is here, then you get dp by dy is equals to minus rho g. So this is the governing equation for fluid statics corresponding to an ordinary differential equation representing the pressure distribution as a function of the solution of this differential equation is pressure as a function of y, and this is the governing equation for fluid statics. After the derivation, let us go to the analytical solution for this ordinary differential equation. Now, to do that, let us consider a fluid column. Let us say that this is a water column, and this is our governing equation. dp by dy is equals to minus rho g. Let us consider 2 points, 1 and 2, and the spacing between these 2 points is h. y2 minus y1 is h. Now, to obtain the analytical solution, it involves basically you have to integrate from P1 to P2 and Y1 to Y2, and once you integrate, here you get P2 minus P1 is equals to minus rho g Y2 minus 1 Y1, which is h, and finally you get P1 is equals to P2 plus rho g h. So basically what you are observing is the pressure on a deeper layer is basically it balances the weight of the fluid which is above. So on a lower layer, pressure is more as compared to the upper layers. So this is the pressure distribution. Now, if you consider the pressure on the free surface of this water column as atmospheric, then what is shown here is the distribution of the gauge pressure. The gauge pressure is 0 here because with reference to atmospheric pressure at the free surface, you have a gauge pressure of 0, and it increases linearly as you go below. So the gauge pressure distribution is shown here, and the absolute magnitude of pressure at point 1 equals to P atmospheric plus rho g h. So as I mentioned, the physical interpretation of this analytical solution is the extra weight of the fluid in the deeper layer is balanced by the increase in the pressure. As I had shown in the derivation also, that when we did sigma Fy is equals to 0, basically the pressure is balanced by the gravitational force. So the gravitational force is acting in the downward direction. To balance it in the deeper layer, the pressure has to be larger. Now, I will show you, I'll take an example problem as shown here. Let us suppose this is a tank of very arbitrary cross section, and this is to show you that the pressure at a particular height is independent on the shape or the cross section of the solid surface on which it is acting. So if you consider this tank filled with water, and the bottom surface you can see it is made up of this funny shapes, and let us consider points which are on this horizontal line. Let us suppose we are considering two different fluids. Here we are also considering at this region, you have another fluid which is in mercury. And in the remaining part of the tank, you have water. Now let us consider this the height, and we consider certain points. So note that all these points which are located at different points in the bottom surface, but they are located at the same height. So for all these points, as discussed in the previous lecture, if you draw the direction of pressure or at these points, the pressure acts, it's normal and compressive on a solid surface. Let us consider two more points, H, which corresponds to the region where you have mercury, as shown here. This is the point H, and another point I, which is shown here. And these are the direction of pressure on for the various points A, B, C, D, E, F, and G, which is located at the same height, H. And since all these points are in the same fluid, which is water, so they are, although the direction is different at this point, the direction of the pressure at this point is different, even then you can see that their magnitudes are same. Whereas if you consider the point H and I, which are also located at the same depth, but the point H is surrounded by mercury, whereas point I is surrounded by water. So although they are located at the same height, point H and I, and although the direction of pressure force is vertical at both the points, even then these pressures are not same, because this pH will be equal to the density of water divided by rho GH, where density you will consider is corresponding to water. And then for the smaller height, you will consider the density of mercury. So the weight here at this point will consist of the weight of upper layer of water as well as mercury. Whereas if you consider this point, it considers the weight of only water. So that's why, since the weight which it needs to support is different, the pressure at these 2 points are different. This is just to demonstrate that the pressure is independent, acting on a solid surface is independent of the cross section and the direction of the solid surface. It is considered the Pascal's law, which states that pressure applied on a confined fluid increases the pressure throughout the fluid by the same amount. So this is another characteristic of pressure which is represented by a law which is called as Pascal's law. That if you consider a fluid which is in a closed region, and if you apply certain pressure in some region, then for the complete fluid, throughout the fluid, the pressure which you are applying leads to an increase throughout the fluid. To represent it, let us consider an example of an hydraulic jet, where this is the container, and at the top I am showing you a piston, a smaller size of the piston on the left side and the larger size of the piston on the right side. And then this is filled with oil. Now, based on your capacity, you can apply certain limited amount of force. So you can have you can create a pressure which is represented here as P1 A1, where A1 is the cross section of the so you're basically increasing the pressure by F1 by A1. So although this F is relatively maybe small, and with this you increase the pressure maybe by a small amount, but although the small amount of pressure, because that pressure gets transmitted throughout the fluid, so that even the small amount of pressure here, when it gets transferred here, when you multiply by the area which is much larger, it leads to a much larger force. So by applying a smaller force and a smaller pressure, you can transmit a much larger force, and that can act to even lift a car. So that's the principle which is used in hydraulic jet. So this represents another characteristics of a fluid which is stationary, that when you apply even a small pressure, you can create a setup so that it can transmit a large force, and that can be used to lift heavy objects such as car as shown here, which we commonly used in hydraulic jet. With this, I come to the end of this lecture 8 on Governing equation and its solution on the topic 2 on fluid statics. Thank you for your attention.